In this video, we're going to continue our discussion of periodic trends by talking about ionization energy. Ionization energy is the minimum amount of energy required to remove an electron from an atom or ion in its gaseous state. So the minimum energy required to remove an electron. And it tells us how strongly an atom is holding on to its outermost electrons. And the trends that you're going to find on the periodic table are that as you move up a group or family or across the period, there will be increasing ionization energies. Moving across the period, valence shells become more stable. Why? Because the effective nuclear charge becomes more stable. Recall, the effective nuclear charge is that nuclear charge minus the shielding effect that occurs. And as we move across a period, we're adding protons to the nucleus, which is increasing the effective nuclear charge. However, the electron shielding remains constant moving across the period. As we move up a group or family, there's a decrease in electron shielding because as we move up from, say, n equals 4 to n equals 3, what's happening? The atomic radius is getting smaller and smaller and smaller, which means the internal electron shielding is decreasing. It means the outermost electrons are now getting closer and closer to the nucleus. Let's look at this graph of ionization energy as a function of the atomic number. The units for ionization energy in this case are electron volts, which are simply a unit for energy like megajoules per mole, which is another very common unit of energy used when discussing ionization energy. I want you to look at hydrogen, helium. All right, lithium, beryllium, boron, carbon, nitrogen, oxygen. What's going on here? Fluorine, neon, way up there. All right. So we see that this trend, there are some exceptions to it, which is why throughout our discussion of periodicity, I've used terms like usually and generally. Noble gases possess the highest ionization energies relative to other species because they have a full valence shell. Now, for electronegativity on the Pauling scale, they didn't have a value. And we said that's because they already have a full valence. Now we're saying they have the highest ability to basically hang on to their electrons because they have a full valence. And that's going to be something that comes up over and over again. Ionization energies often are measured and the different levels, okay? So depending on the chemical species, there are multiple ionization energies. And these are typically articulated as ionization energy 1, ionization energy 2, or the second ionization energy, the third ionization energy. And in this table here, let's look at sodium. So for the first ionization energy, there is a value of 495 megajoules per mole, okay? And when we move to the second ionization energy, we see an increase, orders of magnitude larger than the ionization energy for number 1. And you will see that throughout this table, orders of magnitude greater. And the reason for that deals with Coulomb's law. Now, we can also express this as an equation where one atom in its gaseous state plus that threshold, that minimum amount of energy in this case ionization energy 1, yields the cation in its gaseous form. Because it's losing an electron, it'll become a positively charged ion along with giving off that electron. Let's look at this Bohr model here. Sodium. Let's talk about this outermost valence electron, and that's corresponding with this value here in the table. So 495. That's the amount of energy required to basically to remove this electron. All right. So once that occurs, we drop down to this shell. And this shell is considerably closer to the nucleus. So that means there will be a greater effective charge, and we're also going to see the Coulombic attraction, that inverse squared relationship. We're going to see distance go down, which means the amount of energy or electrostatic force goes way up. And that is based on Coulomb's law, which was discussed briefly in the last video. So we have continued our discussion of periodicity. Now you've talked about atomic radii, ionization energies, electronegativity, electron affinity. I wonder what could possibly be next. I'll see you guys in class.